Hi folks, so I hope this video finds you well. In today's lesson I'm going to do my best to teach you graphical derivatives, and it is aligned with the CED 2.4.1. And our main issue today is we're going to define basically what it means to be differentiable. We're going to talk about how we can derive a derivative graph based on the original graph. Just by knowing a couple of things about the slope and how it relates to the function. So let's take a walk through, or let's just walk through these notes. It says that as we saw previously, the derivative gives us a formula for the slope. So we need to start thinking about those two words interchangeably. Derivative gives the formula for the slope of the tangent line. Since tangent lines always point in the direction of the function, then the slope of the curve is the same as the slope of the tangent line at that point. So, if a line has a positive slope, then the line itself is increasing. All right? If a line has a positive slope, I'm trying to do this right on the camera, then it is increasing. Let's see, would that do it or would that do it for you guys? So anyway, you can kind of think of that on your own. If a line has a positive slope, then the line is increasing. Now that only works with lines, right? But let's talk about the derivative of a function. Well, the derivative of a function, if the derivative of, let's say, f of x is positive, then the function itself is increasing. The derivative of a function is positive, then the function itself is increasing. Well, if the function is increasing, then what can we say about the derivative? Well, if the function is increasing and it's going up, well, then it must have a positive slope. So that's what we say. We say that the derivative is positive, or the function itself has a positive slope. Okay, I want to make a very important note over here on the right-hand side. So take a minute and jot that down. And I'm going to try to stay on this for just a minute so that we can talk through it. But note, the word positive and the word increasing cannot be used interchangeably. It almost sounds like I'm using them interchangeably during these notes. But the word positive and the word increasing mean two different things. The word positive means that you are above the x-axis. The word increasing means that if you look at one point and you look at the next point to the right of it, then that next point to the right of it has a higher y value. Okay? So please make sure that you have that note and kind of commit that one to memory. Okay, so here are our big ideas. We've said that basically, those two ideas, if the function is positive, the derivative is increasing. If the derivative is positive, the function is increasing. And now we're going to say the same thing about negative. If the derivative is negative, the function's decreasing. If the function's decreasing, then the derivative is negative. All right, so how does this come into play? Well, let's look at an example. For now, we're just going to call points A and B on the graph. We're just going to call them turning points. And at these 2 points, we can see that the derivative is 0. I've even labeled it there for you. Okay? If the derivative is 0, then the situation is a bit more complicated. It's not increasing or decreasing at that point, right? So if the function is turning around, then the derivative will be either 0 or undefined, as we'll see later. But however, if the derivative is 0, then the function itself might be turning around, it might not. Now in both of these examples, A and B, they both are turning points. So let's look at a graph that does not have a turning point. So this is the graph of y equals x minus 3 cubed plus 2. All right, so y equals x minus 3 cubed plus 2. So I gave it a vertex. I call it a vertex, but this little point right in here, that's where we are going to have a 0 slope. And you can tell by this tangent line right here that that tangent has a slope of 0. So in other words, y prime, oops, not sure what happened there. Okay, so y prime at x equals 3 is 0. Okay, but the function itself doesn't turn around in that case. So anyway, that's that. So let's take a peek at the definition. The definition of differentiability, or and here's what it says: a function is differentiable at x equals c if and only if the function meets the following requirements. The function must be continuous at a given point, and it must not have a corner cusp or vertical asymptote. The way I do that is I just check to make sure that the left-hand side, the left-hand slope, is the same as the right-hand slope. Okay, so if it's a piecewise function, you might not be able to tell very well if it's a corner or not. Zooming in helps, but sometimes it's still pretty close, or sometimes you don't have a graphing utility. So basically what you want to do is make sure that the slopes are the same, so that you don't have a corner. So here's an example of a corner, a cusp, and a vertical tangent. Okay? The derivative of a function is undefined at all of these places. Okay? That means that the function itself is not differentiable at a corner, at a cusp, or at a place where there is a vertical tangent. So it is differentiable otherwise. There's a little bit here that I needed to show you about this graph again. Well, okay, I think I talked through this. F prime at 3 equals 0, but the function does not turn around. Okay, yeah. All right, so let's take a look at another definition. Another definition is called, this definition is called a critical point. Some people just call it a critical value. Okay, I lost my train of thought there, but here's what I'm going to tell you. A critical point is a critical point, but it's also called a critical value. Okay, so even though it says the word critical point, it doesn't always mean that it's a point like x comma y. Typically, when they say critical point, they're still only talking about the x value. So they're kind of used that interchangeably, and I think that that's a little bit annoying. I think that they should use the word value instead of point, but in some cases they'll say this is the point at x equals 5, and you're going, well, that's not a point. Well, okay, anyways, here we go. A critical point is a point at x equals c such that the derivative equals 0. Now, see if you can read that one out loud. The derivative equals 0 at c. Or the derivative is undefined at c. Okay? In other words, a critical value on a graph will be at a turning point, or it'll be at a corner, cusp, or vertical asymptote. I'm sorry, vertical tangent. So, finding the graph of f prime from the graph of f. Now, we won't really have to do this, I guess, finding the graph until a little bit later in the semester, but I think that it's important to show you this now so that you can get the idea behind when a derivative is equal to 0. Okay, so here goes. So this says to find a possible graph, draw an f prime number line. Make sure you label your number line. The first points we put on any number line are places where the function is 0 or undefined. Really, I should say the derivative is 0 or undefined. Here we are looking for places where the graph turns around. Next we look for the positive and negative places for f prime. When f is increasing, we'll put a plus sign. Plus sign means positive. It does not mean increasing. Okay? All right, if you want to make your little note there that it means positive, it doesn't mean the word increasing. Okay, and then if f is decreasing, we put a negative sign, and that just means negative. It does not mean decreasing. Okay, when I say negative, I mean less than 0. All right, when I say positive, I mean greater than 0. That's another way of saying it. Okay, so let's take a look at this problem here. We're going to make a number line. Hopefully I can make a nice and straight one here. Ba-boom. Okay, and on that number line, actually, let's make it a little thinner. There we go. I want you to label x on the bottom and f prime of x on the top. This is going to be our f prime number line. All right, and what we do is we start off on this function, and it looks like to me that on the left side of -1, f itself is increasing. So if f is increasing, then what we said about f prime is that f prime would be positive. So we're going to go down and at -1, we're going to say that f prime is 0. But on the left side, let's see if I can make a 0. Okay, but on the left side of that, f prime is increasing. So I'm going to go ahead and put my plus sign. All these values are above 0. That's what that plus sign means, remember. Greater than 0. All right, so then what happens is we're going to just continue following this and then until there's another change. So this looks like we're decreasing, and we decrease all the way until we get to x equals 3. So over on my number line, I'm going to go out to x equals 3. Maybe I could go a little bit farther out to match that graph, but that's okay. Here's your 3, and at f prime we're going to get 0. Now what happened between those two? Well, between those two, the function itself was decreasing. So I'm going to write the negative symbol there. Okay? Decreasing. Now, the function decreasing means the f prime is negative, less than 0. All right. After 3, it appears to me that this function is always going to be increasing after that. So we're going to put a plus sign because f prime would be positive. So what we're going to do then is we're going to sketch this. So we're going to go over to -1, and we know that at -1 we should have, what is it called, an x-intercept. On the left of 1, it should be above the x-axis, and to the right of -1 it should be below the x-axis. And then we're going to go out to +3. 1, 2, 3. And at +3, this is showing me that the function needs to return from the negative side and then go back to the positive side again. So negative side would be underneath the x-axis, and then the positive side would be above the x-axis. Now the next thing that I do is I try to determine what kind of function I'm using on the left-hand side. So what kind of function do you imagine this is? Well, it's definitely an odd function, right? And it hits the x-axis 3 times. The reason I know it's odd function is because even functions, they open upwards like this. Their end behavior matches. And they also match below if it's a negative even function. So this is an odd function, has a positive leading coefficient. So in this case, let's call this, I don't know, something to the third. It's not x to the third, but something to the third. So if that's to the third and we're taking a derivative, then I'm expecting to get some kind of quadratic. So instead of calling it cubic, x to the third, maybe I should use the word it's cubic. And on this one, maybe I should say the word quadratic. Seems like my pen wants to erase anytime I circle something. So there we go. This one is quadratic. Okay, so let's go back to that black pen, and just basically we just need to connect the dots with a nice smooth quadratic curve, and this will serve as our sketch of the derivative graph. Now that's kind of strange to think of because we typically find the slope, and the slope is a number. That's not the case anymore. The slope is actually a function now. Okay? So let's take a look at this one. I don't like to skip the number line. So we're going to actually do the number line, and then we're going to come back to this function here. So let's see. We're going to go out to -2. That's our turning point. And I see that the function itself goes from decreasing to increasing. And then at 1, that's a turning point, and that's when the function goes from increasing to decreasing. And then at -3, I'm sorry, at +3, the function goes from decreasing to increasing again. Okay? So our number line, well, I told you that I would use the number line, and now I'm kind of going against what I really want to do due to time constraints. So let's go out to -2. Let's go out to +1 and to +3. And all three of these should be x-intercepts because that's where the derivative is equal to 0. Alright, if the derivative equals 0, then that means that we're going to get an x-intercept there. So at -2, it went from decreasing to increasing. So over here it needs to go from minus to plus. So from minus to plus, I'm just going to connect this with a little line segment, a miniature line segment there. Then we're going to go out to 1, and it goes from increasing to decreasing. So there's your plus sign already, and the minus sign will be here. So plus to minus. And then at 3 it goes from decreasing to increasing, so from negative to positive. And then I go back and I think, all right, well, what kind of function is this? It appears to me that it's quartic, or it could be to the 6th power or something, but look, it hits 1, 2, 3, 4 times, so there's quite a bit of evidence for me to think that this is a quartic. If you go down 1, then that would turn it into a cubic. Okay? Because remember, when we take derivatives of power functions, the power actually reduces by 1, right? So what we'll do is we'll just make this a nice cubic function. A cubic function that hits the x-axis 3 times in this case, and maybe not make a nice curve like that. So there's your cubic sketch of f prime. Okay, so the last example I believe is the toughest example, just because. All right, so the idea of a derivative, remember, is that the derivative is the slope. And if the derivative is the slope, then and you have line segments, then actually you can just find out what the slope is. So let me show you what I mean. I know that this over here is decreasing on the left, but I can actually tell you what the slope is. The slope is -2. All right? And I know that it's increasing here, and I know that this would have been a turning point, so that I know that the derivative at a turning point like that, well, at a sharp corner like that, is actually undefined. F prime at -2 is undefined. All right. And then it goes flat, so this is like a slope equals 0 kind of a thing. And then it's not increasing or decreasing, but over here the slope, I can tell that the function is decreasing, but I can also compute the slope. I know what it is. It's down 4 over, is it down 4 over 1? So -4. Okay, so from there what we're going to do is go ahead and plot our let's see, we should probably plot all of our corners, right? So this is f prime at 0 is undefined. This corner, f prime at 3, is undefined. So if you've made it this long through the video, man, I should give you a cookie, because this is the hardest part, and it's at the end of the video. I should have put this in maybe a separate video, but here goes. So we're going to go out to -2, and we know that the function itself is going to be undefined, or the derivative is going to be undefined there. But if its derivative is undefined there, I can't put a dot. Okay, so we just need to keep that in mind, that there is no point on f prime equals -2. Sorry, f prime of -2. So same thing about this one. At 0, same thing at f prime 3. So at 3, we need to make sure that the function does not touch these lines. All right, and you could say the same thing at the end points, but let's let's start here. The slope is -2 from -4 to -2. The slope is -2. Well, if the slope is -2, then I can just go out here to -2, draw one of those holes, if the computer lets me, and then we're going to go out to the right and draw another hole. If you do an open dot, then that means it's not defined there, so we're still accurate here. I never found the slope, it looks like, right in here. So the slope is 1 up 2 over 2, so the slope is 1. If the slope is 1, then that means that my output will be 1 on f prime, all the way up until I get to the y-axis, or the f prime axis. Then it jumps down. The slope is 0 right here. If you have a flat line, then f prime equals 0. So it's going to equal 0 all the way from 0 to 3. So from 0 all the way up to 3, the derivative is 0. So I'm just going to make that a little bit darker so that you can see the derivative graph there. And then it's decreasing, but the slope is at -4 from 3 to 4. So from 3 to 4, the slope is at -4. From 3 to 4, the slope is -4. So that is the hardest example that we've done, and it ends up being a piecewise function, and I want to see if this kind of makes sense to you. So if this graph over here is made up of a bunch of chunks of lines, okay? So what is the slope of a line? Well, the slope of a line is always constant. Okay? So we have a bunch of line pieces, and we have a bunch of constant pieces, okay, when we take the derivative. So I did my best, you guys, to show you how to connect the graph to f prime. But really, the main lesson today is, where can a function be differentiable? All right, the function is only differentiable if the function is continuous and it does not have a corner, cusp, or vertical asymptote. All right, a derivative is undefined at those corner cusps and vertical, I said asymptote again, vertical tangent. Okay, all right, bless y'all. We will see y'all in another video.